Okay. This is a webinar series of Sapienza Neuroscience for 2025. This is a very special event for most of us. It is a memorial webinar on Professor Florinda Ferreri, who passed away 2 years ago this day, September 3. And it's important for most of us to remember the important impact for our professional life of Professor Florinda Ferreri, who was an associate professor of neurology in University of Padua in Italy, and was a pioneer of clinical neurophysiology using transcranial magnetic stimulation and simultaneous ongoing EEG recordings in patients with Alzheimer's disease and control subjects. He provided the first evidence of abnormal excitability of the cerebral cortex in these patients by means of this advanced new approach, today used by a lot of researchers in clinical neurophysiology. It's my pleasure to introduce the seminar today by Professor Camillo Porcaro. Is an associate professor in bioengineering at the Department of Neuroscience of the University of Padua, Italy, the same department of Professor Florinda Ferreri. And Professor Porcaro is an expert of computational neuroscience and computational clinical neurophysiology with a lot of outstanding contributions in the source separation from electroencephalographic and magnetoencephalographic data, and innovation in the field of analysis of complexity of EEG signal for clinical applications. The title of his presentation is Beyond EEG Oscillations in Pathological Conditions, with a focus on fractal dimension. So it's my pleasure to invite Professor Porcaro to share his presentation and start the presentation. Is expected a presentation of 40 minutes, and at the end we will have a brief discussion. Thanks a lot, Professor Porcaro.
Thank you, Claudio, for inviting me. So just a check, because I don't have the... are you able to see the presentation in the correct way?
Yes.
Okay, thank you. So it's really a pleasure for me to do this presentation in memory of Florinda Ferreri. As Claudio said, I was really linked with her from a long time, starting from Rome, more or less 15, or I don't want to say 20 years ago, just because otherwise I become too old. But very, very linked with her. And then when we have this possibility to work together in Padua, we start to work on some physiological data, starting with this this publication, or this analysis on epileptic patients. We were let's say, involved in this story to create a laboratory for this kind of patients. But unfortunately, we just have the time to finish this work. And I want to remember Florinda, to be honest, on Palermo a couple of years ago when we start to work with this data set. And it was a nice, we were in the hall of the hotel working on the data with the computer, MATLAB, and whatever. And at some point, Florinda says, but so all the time that you change a subject, you have to change all the script, all the parameters. So you have to do, you cannot apply all the time the same things. And then they said, yeah, of course, this is the problem of electrophysiology. And she said me, so my husband was right, but please don't tell him that I say so. So this was Florinda, super nice person, always, very ironic all the time. And another point that we were developing here in Padua was the part related to TMS EEG, one of her excellence or let's say expertise. I'm quite sure that she loved this kind of paper investigating the TMS EEG in the pre-stimulus to predict the post-stimulus. Unfortunately, we were not able to do it because the time was not enough for her. So before we start to cry, sorry for that. But back to the science. I will introduce these two kind of results. But before starting these results, I would like to introduce some topic linked with both of the publication and this the fractal dimension. So I hope that there are a lot of students listening this talk. So I will also introduce some basics. I already apologize for the people that already know some of these slides, but the time was quite short to make this presentation, so I recite some of them, but only the part that I really think that is very constructive for the presentation. So what we are going to do, the title is Beyond EEG Oscillation in Pathological Condition, even if for the EEG TMS we are going to investigate the healthy condition. But the content of the presentation are divided in three parts. The first part is the brain oscillation, the importance of the waveform shape, just to make the point why we need the other kind of measure respect to just investigate brains or brain oscillation like we know, like a sinusoid oscillation. And then we introduce the fractal and fractal dimension, starting from the geometry of the fractals, and after we move to the fractal dimension properties, and after we do the last part is the one where we use which fractal dimension, that is a method for estimate fractal dimension in some pathological condition. That is the flow of this 45 minutes. So let's start with this oscillation story. So I choose this paper because it's really nice. It's very funny from Klonowski, and he make this kind of paper just using question. I just cut and paste some of them that is really interesting, and then is mainly is EEG a linear signal? And it's very strict, say no, EEG signal generated by brain is nonlinear. And other point are that EEG are non-stationary, non-linear signals, we already said. And then why we need or why we still using a linear method to analyze non-linear signals. Other question is if EEG is a stationary signal, and as he already said, is non-stationary, non-linear, and noisy. What we already know about the EEG signal, but also the MEG signal, that we recognize that this kind of signal are very noisy. And probably the success of the independent component analysis in 1996 was just because this kind of method were super good in cleaning the data, but we make some resistance in this concept of non-stationarity and non-linearity, yet, at least. So there is also this nice paper that I suggest people that are interested in this kind of topic to have a read. And this is also the title of my content, Brain Oscillations and the Importance of Waveform Shape. And he's in this paper still say that even if the study of the oscillation are very dominant feature from the brain recordings and play a key rules for communication and neural computation, however, we have to understand that this kind of signal are not sinusoidal. And here I want to remember some discussion that we did with Franca Tecchio, that is also my supervisor for the PhD, during my PhD with Filippo, and also we worked together when I was in Rome regarding this sinusoidal signal and how we can work on it. And what I realized at some point that the filter, when we filter the data, we induce an oscillation in centered to the 0 point, and then we induce a sinusoidal activation of the data, but probably we are making some, let's say, error in the data. Other thing that we want to understand, and you can find very well in this publication, when there are a lot of examples on many kind of electrophysiological data that are non-sinusoidal. But instead, when we have to realize that when we use fast Fourier transform, we hypothesize that the decomposition in frequency is on the sinusoidal frequency. So I think we have to keep in mind that there is some error that we introduce in our analysis. This is back to the Klonowski paper, as we say the question. I want to make this example that when I discovered it, I was quite impressed. And the story is that if we use a linear method like FFT, as I say already, we are inducing that we are analyzing sinusoidal data. But the most, this example that I would like to emphasize or to highlight is that if we took a alpha oscillation, this is a real recording session activity of the EEG, we can say that it's very similar to this stereotype analysis. This is a synthetic data. And the synthetic data, as you see here, are built by a sinusoid around 12 hertz and multiply, or let's say, convolved with a cosinusoid. And we get this kind of signal that is very similar to the bars of the 10 hertz or 12 hertz oscillation. However, when we apply fast Fourier transform, what we get is two sinusoids, so two frequencies, one at 11 hertz and the other is at 13 hertz. So as you see, if we have a spectrogram here, we had a 11 and 13 hertz peak. So we completely miss the main frequency of the original data. So this is what means using a linear method that hypothesizes a linear oscillation or sinusoidal oscillation, and instead we don't have, because probably the activity recorded from the brain are not linear. So this is just highlighting what is the legend of the figure, but it's more or less what I already said. So the point is, do we need other measure to characterize brain dynamic? Yeah, the answer, at least from my point of view, from some of the people that are listening, at least for Filippo, Franca, I think, the answer is yes, we do, mainly because more and more evidence shows that brain rhythms are not rhythmic and electrical recording from many brain regions at multiple spatial scales with neural oscillations that are not sinusoidal. So we need some method that is not sinusoidal, that not assume that the signal is sinusoidal for investigate, or as I say, I like to say that to better extract or to extract more information, also the nonlinear information that we get from the EEG or MEG recordings. The paper that is emphasized this point is this paper, a very nice paper, is very well written with a lot of example, practical or real example, and also mathematical explanation for what he say in this sentence. Very interesting paper. I really recommend to have a read or look for it. So we make the point of why we need this nonlinear method, and then we passionate on fractal. Of course, fractal dimension is not the unique measure that is nonlinear, but I'm passionate on that because since that is work very well with using a few parameters that we need to tune for having the information. As I have a discussion already in Copenhagen with Filippo Zappasodi, we discuss a lot about the other methods that can be also nice to use, but always we have parameter, or let's say that we have to tune to get the proper information from the data. In my opinion, if we make some knowledge, or we understand how to work with the Iguchi fractal dimension, I think the Iguchi fractal dimension is the more stable and more, let's say, parameter-free regarding the other method that now I'm going to show you. But before all, we move to this fractal. So the perception of the fractal is mainly on this kind of images, mainly on 2D images, where we can see one figure that is replicated infinite time with different scales. So in fact, this is the exact definition of fractal figure in fractal geometry. We have many and many kind of different figure, very nice figure for fractality. However, we don't have, what I want to say that we don't need to perceive that is just synthetic data, because sorry, before that I want to explain what means generate a fractal figure. So the fractal figure is based on an initiator in 1D, 2D, or 3D, and after we have a generator like this. This is a generator of in 1D, 2D, or 3D, and after we have a number of iterations. What means this, if I can take a pen, means that we apply this generator to this line, and then we have this situation over here. And after, if we apply to this point, we have this operation over here, 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 and here. And then on each line, we apply the generator, and what we get is this kind of figure that looks really replicated, very nice. And we have a fractal figure. What I said before, we don't need to perceive that fractality is just in synthetic data, because nature is full of fractal objects. I know that already Franca is already smiling because I show this nice figure over here, that she is one of the first that she liked and look for in the Mercato. I remember in Rome to find this kind of cavolo romano that is super fractal, if you see here. But there are many, but not also we have fractality in our body, but not only in our body, in many parts of our brain and whatever, but also in our signal. And in a few minutes, I explain what means in the signal that we are recording using EEG or MEG. But before all, since I saw that there are some students, I want to make the point of what fractal geometry or fractal dimension are measuring. I use always this example, sorry for the people that already saw, but I found and I have a lot of feedback that is very useful, so I repropose this kind of example. This example is, they start from the idea how we can measure some objects. So now we have measure unit to measure the objects, or we can change the idea how to measure, and then we can say that the object A here can be measured by an object, or maybe the object B can be measured by an object A by a scale factor K. So what means this? We means that B is equal to A by K, and then if we have that A, our object, our first object is equal to 2, and our scale factor is 0.5, half, we have that B is equal to A by K, then B is equal to 1. This is another way to measure an object starting from another object. So what we have for length, we have that the size is, the length is a measure of size by K powered by 1. For the 2D object, so for this triangle, for the Euclidean geometry, we have the base, so B by H divided by 2, we have the area. Or otherwise, we can apply this method, and we can say that B is equal to B by K, so the base for the H by K, divided by 2. What means this? Means that if we do some algebra, that K powered by 2 is equal to B by H divided by 2. But this is equal to A. So B is equal to K powered by 2 by A. Exactly what this. So if we have A with a measure and the scale factor is always 0.5, what we have is that the B is equal to A divided by 4. So this, we measure B starting from A. Then the rules is that area is equal to size by K powered by 2. So to make the long story short, for the 3D, we apply the same rules. What we get, that volume is size by K powered by 3. As you see, I'm sure that you already noticed that for length, we have K powered by 1, so the dimension. For 2D object, we have 2, and for 3D object, we have 3. So this means that the power of K is representing the dimension of the objects. But let's say we know the rule for the 2D objects, but if we apply this rule, so we divide this triangle A and we eliminate the triangle 4, that is exactly the triangle B, as we say in this representation. So for triangle A, we delete the triangle 4. Then we apply, as we say, so we have triangle 1, 2, and 3, and here we have empty space. So if we apply this rule, as we said before, many times, what we get the Sierpinski triangle. Now, let's try to understand if this object is a 2D object or a 1D object. To measure that, we apply the rules that we learned just before. We apply a K scale factor, and we say, based on the rule, that B is equal to A by K powered by 2. But this is true just if we are sure that this triangle is a 2D object. For now, let's say this 2 like an unknown variable, and we call D. Then we say that B is equal A by K powered by T. Then, if we do that A is equal 3 times B, as you can see here, that A is 3 times B, then if we make some algebra over here, just to be very long or short, so we say that we make some algebra over here, and we explicit by 2 powered by D equal to 3. So what do we get from here? We get that if D is equal to 1, we have 2 equal to 3, that means that is impossible. Then if D is equal to 2, we have that 4 is equal to 3. That still is impossible. So this triangle do not have dimension 1, neither 2. So which is the dimension of this triangle? To move to the dimension of this triangle, we have to move to the logarithm base. Then we apply the logarithm base here. and then means following the rule of the logarithm, we said that d is 2 powered by d is equal to d by logarithm of 2 equal to logarithm of 3. And then if we isolate d, we have logarithm of 3 divided by log of 2. And this means that d is equal to 1.585. So this is the dimension of this triangle. So this triangle is a fractal figure, is not Euclidean measure anymore, and cannot be measured by Euclidean geometry, but we have that its dimension is something that is between 1 and 2. So fractal is, in any case, means something that is fractal, then is something that is not an entire number. So this, I think, is in a way very easy to understand what is fractal means. This is an explanation even more in deep, but I don't think we need. So we start from the rule, and then we generate B and A are our object. We divide B and A, we call L. Then we make the logarithm transformation, and then we have the fractal dimension that is always the log of the proportion between B and A and the logarithm of K. That is the scalar factor. This is something that we have here, and measure something or all the objects that are in between 1, 2, or 2, 3. But what does means this when we are, if we are working with electrophysiology, and then we are recording electrophysiological data? So for now, let's say EEG data. So EEG data are time series data, and then what we have, we need to understand that there is also a way to measure time series with a fractal dimension approach. So yes, and this is what you can find in this chapter book. And we share all the code to do all this analysis in our GitHub. In a few minutes, I'll show you the link. And we simulate a random noise and a ramp. I simulate these two, let's say, time series. Of course, these are synthetic time series because are the two, the lower upper bound and the lower bound. So this is a phi or a time series that has a fractal dimension equal to 1, and the random noise instead is something or a time series that have a fractal dimension equal to 2. So all the other time series that are between a ramp or a random noise can be fractal, so can be between 1 and 2. So this is the, just to be sure that you understand, this is the upper bound. So there is no other time series that is up to 2, and there is no other time series that is lower than 1. We can simulate other time series like with the Weierstrass cosine. And one thing that is very interesting to make like a property between fractality and other measure that now we are working more and more in Padua is if we are able to find a relationship between fractality and other measure. And this is very known way. So there is this inverse relations between memory and fractal dimension. What means? Means that lower memory means means lower FD, higher memory means higher, sorry, it's exactly the opposite. So lower memory, when we have higher fractal dimension, we have lower memory, just sure, and the opposite. What means? Means that if we have a random noise with a fractal dimension equal to 2, we, of course, we understand that we are not able to predict this time series because this is do not have memory. What means? Means that analyzing the data before, we are not able to predict the data after. Instead, for a ramp which has higher memory, so lower fractal dimension, because in fact here we have fractal dimension, the lower one that is equal to 1, because if we know the first point or the second point, the third point, we are able to predict completely the time series that we have in a ramp condition. Hopefully I was very clear, hopefully, but otherwise we can have some discussion later on. So there are many ways. So because here the question is how can we generate synthetic time series with a known fractal dimension? There are many different ways to do it. And why we need this? We need this because if we want to understand how stable, how powerful is the method of the estimation of fractal dimension, we need to know a priori the fractal dimension of the time series, because otherwise we never know if we are estimating the correct measure. So we have the wavelength cosine, the Tagashi function, fractal Gaussian noise, and fractional Brownian noise. All this code, all this function can be found here in the GitHub that we share with all people that want to download the code. You can generate this kind of time series with different fractal dimension, with different kind of simple frequency. You can change many parameters over there. You can generate your synthetic data. And then how we can estimate the time series. There are many different ways to estimate the fractal dimension. These are few of them, and probably the more used, and are the slope power spectral density, the trend rotation analysis, the Harst or generalized Harst exponent, the Iguchi fractal dimension, the Katz fractal dimension. And what we did here, you can find all the code also for this testing in this in the GitHub. We test the estimation of the methods. Here we have you have all the method, and each line indicate each kind of estimated or synthetic data we simulated. So as you see, we did for many different fractalities, starting from 1 to 2. So with point 0.1, so we have 1.1, 1.2, 1.3, and so on and so on. And we estimate for each of it the fractal dimension using different methods. So the top should be this dashed line. Of course, this is the theoretical fractal dimension that we should get. So the methods that are more close to this dashed line are the more performing, or they estimate better and the fractal dimension in the synthetic data. So you see, the best seems to be the DFA and the Iguchi fractal dimension, less for the Iguchi fractal dimension for the red line, that is the fractal Gaussian noise, that tend to be higher. So for the method that is estimated, tend to be always equal to 2, because if you remember, the fractal Gaussian noise is very close to the Gaussian noise. And the DFA instead for the Tagashi function, it seems that is the more far away respect to the other, that is seems that are very pure respect to this kind of estimation. Of course, there are many parameters that you have to tune, and what I have to say that which fractal dimension has just one parameter you have to tune, that is the K value, but we'll see in 2 slides later. So I hope that I give you an overview of the idea of how we can measure fractal dimension. Now we move to the application. For the application, if you want to go in deep in this kind of data analysis, I recommend this application. Of course, is how to say citation, but also the reviewer says that it's very didactic. This one of the comment of the reviewer said that I found this systematic review very didactic, because there is all the first part that explain what means fractal dimension, fractality, and whatever. And after we do the systematic review on some pathology, what we did a systematic review. So we follow the Prisma guidelines. We make some keywords for the PubMed search, and we found some 499 data set of paper. And after we make some refine, and then for us, because we concentrate on EEG, on Iguchi fractal dimension, we found 59 papers that are useful for our systematic review. This is the trend for the 59 paper that we found that there is this increase. I have to say that there is much more, but if we use all the method, but if we concentrate on the Iguchi fractal dimension, this is the trend that we found. Which was the results? The results was that for Alzheimer, we have always that the pathology, so the Alzheimer pathology is always low. So the fractal dimension for the Alzheimer pathology or disease are lower respect to the healthy control age matched. This is very important. I know that is some parameter that sometimes try to be found is very complicated, but for the fractal, especially for the Iguchi fractal dimension, but mainly for all the method that use fractal dimension, age matched is very, very important, because in the next slide I show that it's very dependent from age. The stroke, we found that is always low, and for schizophrenia is always low. So when I say always low, means that the pathology, the Iguchi fractal dimension estimated to on the pathology is lower respect to the healthy control age matched for this pathology. So at the first instance, you can say, okay, so this means for each pathology we have a lower fractal dimension, but this is not the case, because with Frank and Filippo, we did some other study, especially with Frank Tecchio, on the multiple sclerosis, where we can find exactly the opposite, that in the pathology, the fractal dimension is higher respect to the healthy control, but also we have the same trend in Parkinson, that we published, but I didn't mention here, and also in migraine patients. That is something that I not put over here, but the trend is that in that case, the fractal dimension estimated on pathology is higher respect to the healthy control age matched. What means this? Means that if we have that for this kind of pathology, this is a few, but you can find in some pathology that the fractal dimension is lower respect to the age matched, and in some other the fractal dimension is higher. What means this? Means that the healthy control should be in the middle, and this fits very well with the idea of brain criticality. Is something that introduced me, Annalisa Pascarella, in some congress or talk that we have together, and I found very interesting. I'm make more study on this point. And what they say, very well described in this publication over here. Brain criticality refers to the idea that the brain operates near a phase transition between order and disorder. So when you say order and disorder, you mean chaos and not chaos, then complexity and not complexity. A state called criticality, which is thought to be optimal for cognitive function. Then what means? Means that we are if we are healthy, in a healthy condition, we are in a critical point. Then if we have pathology, we can be in subcritical or supercritical. Subcritical means that if you make a stimulation, you have a less, this is just an hypothesis, a less propagation of the information. Instead, if you are in a hypercritical, supercritical, then you have a massive propagation of the information that sometimes doesn't mean that higher propagation is better than lower propagation. This theory says that you should be in a critical way. So always too low or too high is always bad. So we need to be in the middle. This is more or less what I interpreted this story of criticality. The overall of the story, and I won't concentrate just on aging because I already explained something before. So if we do this aging, and this is a figure that is shown for 140 healthy control subjects, but with different age, which is the fractal dimension or Iguchi fractal dimension respect to the age, we have this trend. Then if you are young, you have a lower complexity. If you are in adult age, you have higher complexity, and when you are older, you become lower complex, or your brain become lower complex. This is a kind of trend that already Filippo found in, I remember in the publication, sorry, Filippo, if I don't mention here, but yeah, that is the trend. Also Franca, because there was a publication in collaboration between Frank Tecchio and Filippo. So I replicate here very, very well. And now, if we have still time, sorry, probably it was a little bit longer. So let's analyze the data for epileptic subjects. So here we studied 25 subjects. We age matched with healthy control. And in this case, what we did, we administrate a drug in one phase. We make, sorry, an EEG recording in T1 without administration of drugs, and in T2 with administration of drugs. And we compare with 25 age-matched health control. We have different drugs, but we work on this a little bit later. So what we do inclusion and exclusion criteria. I'm not a medical doctor. Fortunately, at that time was Florinda that recruited these patients. Then my part was on the pipeline for analysis. So this is the pipeline that we use. We extract different features, like standard features that are delta, theta, alpha, beta, and gamma band, and the EF, that is the peak of the alpha oscillation. And then we use also some nonlinear approach, that is the Iguchi fractal dimension. After we did some statistics. What we get? We get that the repeated measure ANOVA get significant results. Then we move to the postdoc, and then in delta, theta, and alpha, we didn't show frequencies that are not significant. And what we get? We get that delta, as you see in this graph, is able to discriminate just between epileptic and healthy control, but not in between the T1 and T2, so before and after drugs administration. Instead, theta seems to be good to discriminate between T1 and T2, but not between 1 and T2. But after drug administration, we are not able to discriminate for the healthy control. And this is what we really want, because we want to using the fractal dimension, using the drug to remodulate the oscillation of the brain activity like the healthy control. So as you see here, this is another case where the drug administration modulate the oscillation of the brain. Instead, the alpha is able just to discriminate between epileptic and healthy control. So theta is something that we are looking for, so discrimination between T1 and T2. And then when we apply the EF, we have the same. The EF is able to discriminate also between T1 and T2, and the fractal dimension is able to discriminate between T1 and T2, so before and after drugs administration. So now we have three features that we can discriminate between the DRT1 and DRT2, and are EF, FD, and theta band. So here we use a Bayesian approach just to understand which is the best feature that better discriminate between the T1 and T2 in epileptic patients. Then, as you see, we get that FD respect to the EF is 195 times better, so more sensitive respect to in discriminating the two, and with theta 231 times. So as you see from here, but also from the p-value, you can see that this discrimination is higher and higher. But it's not just a discrimination, because this is on the average of the data. But despite the conclusion that I already said, for the people that was more, keep attention, here we show the difference between when we use all the drugs instead we use just one drug with the most people, and the trend is always the same. What I want to show is that also in the single subjects level, you see that for theta there is some trends that go down and some trends that go up. Also for the EF, you see some go up and some go down. So it means that before and after the trend, the drug administration, the trend is not always the same. Instead, for the FD, seems that always we get the trend. Maybe can be lower, but it's always lower and go higher. So this is very important, especially when we are going to analyze the single case, because Florinda always told me, yeah, but you work like an average group, but here in the clinical situation, we always work with one person at a time. So we need to find something that works case by single subject by single subject, and that this is was the case, and she was super happy about these results. And if I have still time, I just going to see, yes, I think I probably in a few minutes. This is because this topic is so very was one of the expertise of Florinda, and this is the reason why I just put very in the last minutes is under review. So hopefully we get soon with the second revision. And what we work on this. So the point here was that stimulation of TMS during EEG recording. So it's TMS EEG protocol in the motor area. What we get, this is a map that we get from the data. So I don't know if you are familiar with the TMS EEG, but I'm not going in deep on the methodology. But when you record on EEG and TAP, you have a response after the stimulation that is called map. TAP, sorry, map is from the muscle, it's the TAP. But of course, you have this response after a preprocessing, and the preprocessing can be done by TESA, or there are many different approaches to clean the data. So if you are able to clean and you are good to do it, you have this kind of response. Then mainly the people work on average data. This is the average data of let's say 100 pulse, as you say here, after 100 stimulation. Something that I discussed with Florinda, but unfortunately just in an embryonal way, just doing a coffee or doing a spritz. When we have the opportunity to have the spritz, we start to analyze. I understand, Claudio, that I'm long, but just finish. We start to work on the pre-stimulus, understand the feature of the pre-stimulus that are able to predict the post-stimulus. What we found, divided the pre-stimulus, we analyzed the delta, theta, alpha, beta, and gamma activity. We order the trial based on this pre-stimulus feature. So we order the stimulus that have higher to the lower to higher delta, theta, alpha, beta, gamma. What we found, if we divide it in quartile, first quartile and last quartile, you see that the more discriminative are the gamma activity. I don't want to go in the deep because we are very long. So you see, it means that low gamma have higher response, higher gamma have lower response. And then we keep or back, or is something that we are going to speculate in our paper, that if we have a higher gamma in the pre-stimulus, we are in a supercritical state of the brain, and then the brain is not ready to show or to explain or deliver the stimulus. So you have lower stimulation or lower response. Instead, when you have lower gamma, you have higher response. this is something that we investigate also with fractal dimension, that is just one measure instead of having 5. Then we use, we estimate the fractal dimension on the pre-stimulus, and we predict the post-stimulus. So, and the trend is the same, lower fractal dimension. So higher memory has a better post-stimulus response, lower memory, so higher fractal dimension is not able to make the nice response data. After, and I want to be short, sorry for that. So we make this comparison between the feature that we extract just to understand the relationship that we have between HFD and the other linear method, but this is something that already has been done by Filippo and Franca in some other publication. Here we use a partial correlation, so we clean up all the other interaction between the thing, and then what we found is that the alpha and the gamma are the more important respect that create the or is more linked with HFD. So that means the HFD is not measuring just one component like just one band, but it's a compromise of this band. Just to be noted that the alpha is negative and the gamma is positive. It's something that is correlated but in different positions, not just a linear way. And this is just to reinforce the point. We predict the HFD, so the EEG fractal dimension, using the bands, and also here seems that the gamma alpha is the more important respect to in predicting the HFD, and we did the same using HFD, so HFD, sorry, for predicting the local field potential, so the post-stimulus. And what we get that we predict some machine, we use some machine learning here to do so, and seems that the more important feature are gamma, beta, and HFD, and we did other extra tests that I'm not showing here. If you use just one, or if you use only the gamma, only the frequency band, you are not able to predict well like this, and if you just use the HFD, you are not able to predict so well the post-stimulus. So if you need to use more, so there is some components that are linear and some components that are non-linear, and this is another story that I'm start to study in Padua that is related with the oscillation, that are something that is the oscillation is pure sinusoidal and some other is not sinusoidal. And then we have to divide our data in pure sinusoidal and not sinusoidal data. But this is another story. Then the take-home message, if the only tool you have is a hammer, so just a linear method, you tend to treat everything as if it were a nail. So try to use different tools and treat our data as linear, non-linear, mixed, and whatever. So we can try to get something more. Just thank you for collaborators, and of course, just a hello to Florinda. Thank you.
Thanks a lot, Camillo, for this really exciting seminar on this fractal dimension of EEG signal in clinical neurophysiology. And I wonder if there is a topography of this fractal dimension, if you can see different values in different electrodes, or is a sort of global feature of EEG signal?
Yeah. Thank you, Claudio, for this question. It's very important because I didn't show anything on topography since here mainly we use a clinical application with 19 channel, so it was a little bit complicated to make a clear topography. But we work a lot with Franca Tecchio, but also with Filippo regarding topography or just a region. I know that Franca is working a lot on divide the brain area or Brodmann area and try to characterize that Brodmann area using a fractal dimension. So the answer is yes. If you have many channels, you can characterize channel by channel, and after you can make a topography, and for sure you can, if there is something different across the electrodes, you can find a different complexity. With Franca, we did publication when I was in Rome, and we were able to find a different complexity. For example, in the sensory area or in motor area, they have, like as Franca like to call, fingerprint for each brain area. So you can be able to discriminate also in healthy control or resting condition, this different brain area. What we are doing here in Padua, instead, we are applying, but this is again another story, we are applying the same method in fMRI, in the bold activity, when we make the parcellation, and we know that the fMRI is more selective in space, that has a better spatial resolution, and we are demonstrating, we already published also with Frank when I was in Leuven, we published that there is some resting state network that are higher in complexity and lower in complexity. I just tell you that, for example, primary area are higher in complexity, and high cognitive function like DMN or other cognitive network are lower. And this fit with the connection or the connectivity across the head. So the answer is yes. Little bit longer, but a short answer is yes.
Okay, thank you. And another point is about this complexity measure in relation to the typical indexes of complexity of EEG signal, Leipunkt index, or something coming from entropy, or other nonlinear rates. If there is something specific that you can put in evidence with the fractal dimension.
Okay, so probably you were you review some of my paper, because this is the question that the reviewer always ask. And then always the reviewer asks, but you have to compare, you cannot compare just linear with one nonlinear measure, and then we apply during the review process the other nonlinear measure, mainly the entropy. And what we found also with Franca, with Filippo, but also by myself, that seems that the fractal dimension overperform with respect to the entropy. To be honest, in the paper that I did in Belgium in 2019 regarding the resting state networks in EEG data, we were able to discriminate between primary and high cognitive using the fractal dimension as some index or a combination of some bands. But when we use entropy, the variance was so high that we are not able to discriminate with just the entropy. However, entropy is another linear measure. There are many sophisticated entropy measure that are nonlinear and are able to discriminate between them, but all the time that I apply on my data and compare with the HFD, I found that HFD outperformed the entropy. This doesn't mean that we don't have to use entropy, just say that is overperformed by the HFD.
Okay, thanks a lot. Concerning alpha rhythms in the resting state, we know from animal studies that the frequency of alpha rhythms at the scalp level are related to the frequency of bursting of single neurons in the thalamus, for example, in a sensory thalamus, visual sensory thalamus, or somatosensory thalamus. nuclei, and also at the level of cortical pyramidal neurons in this interaction between the frequency of spiking of cortical pyramidal neurons and the thalamocortical neurons in the sensory thalamic nuclei. And also we know that there is some spectral coherence between the local field potentials recorded in animals in the sensory cortex and in the sensory thalamus. And so concerning the fractal dimension, there is some insight about features of single neurons at the cortical thalamic level in the frequency or in some local field potentials, something that can clarify the neurophysiological feature underlying the fractal dimension that you can derive from the EEG signal.
Yeah, that is a very nice question. And this is the same question that always Maurizio Corbett, that I don't know if is with us, but Maurizio always asking for this kind of question. So we are working on this. We have preliminary results. We try to send in some journal, and we are in revision at the moment. But what we found some connectivity between the subcortical area respect to the cortical one, and what we found respect to the complexity or the Gucci fractal dimension, but not in EEG, that was in fMRI. We found the activity from the subcortical area are driving the cortical area. And what we found also respect to the complexity is that the subcortical one are the more complex respect to the cortical. This is something that seems to fit very well with the hypothesis of this loop, thalamocortical loop. We discussed this in the manuscript, and now we are working with multimodal measure, where we can investigate connectivity directly using complexity measure, since the HFD, the entropy, but also the frequency are univariate measures, so you can calculate channel by channel. So now we are approaching with a multi-level approach, multi-channel approach, just to understand if we can have some proper connectivity linked with the complexity of the signal.
Okay, and
but sorry, the last part is that if you have data, let's say intracortical data, or maybe in animal data that are linked, I'm very happy to analyze this kind of data. But at the moment, I didn't find any database for animal study that are freely available. Then I didn't analyze any of that, but always, but also with Franca, all the time we speak about should be nice to analyze the data also from the complexity point of view in the intracortical data, and maybe not just in human, because I know that Frank already did a publication using intracortical recording in epileptic patient, but in animal, just to characterize if the complexity link with this finding, the neuron finding. But that should be nice. I'm really open to analyze this kind of data. Yeah. Just to keep in mind. Just to keep in mind.
Yeah, it's very interesting. And now the last question is about the robustness of this fractal dimension derived from EEG signal in relation to noise or some artifacts, some, for example, residual artifacts, and there are some measures that of fractal dimension from artifactual data to see if, for example, in periods that you typically remove from your recording, and if you apply your measures to this noisy data with the biological instrumental artifacts, can you see some um,
Yeah.
reasonable fractal dimension values that can confound the analysis
Yeah.
in the data?
Okay. Nice question. Also, this very nice question. To be honest, I never try to apply if I decompose data for cleaning, let's say by ICA, right? And I never apply uh, neither the fractal dimension to the artifacts and neither in the cleaned and non-cleaned data. What I can say, especially for this kind of data that in the clinical data that we analyze with Florinda, they are very noisy. You know that in the clinical situation, especially with these epileptic patients, the data are very noisy. We try to clean using ICA in the best way that we are able to do. However, what we found from the variability of the data, we always found that independently of how well the data are cleaned, the Iguchi fractal dimension seems to be more stable or less variable, less variance in the data of Iguchi fractal dimension. This doesn't mean that Iguchi fractal dimension is robust respect to the noise, despite what you can find in some literature where they state in the paper that HFD is robust respect to the noise. But what noise? Because there is noise and noise. We found that the noise in the paper, in the chapter book that we did and I show in this publication, we simulate the data and we add the noise in decibel. We increase the decibel for the noise, and what we found, but that are synthetic data, that the noise, just when the noise is very high respect to the synthetic data, will be affect the HFD. But if the noise is reasonable, the HFD stay, let's say, stable. However, the activity or the noise in the EEG data are not just random noise. There are very other kind of, there are colored noise. In that case, I'm not confident to say that it's super robust respect to the noise. We need always to be, very pay attention in cleaning the data. That is the first thing.
Okay, thanks a lot. Just a final comment on your comparison between linear measures such as individual frequency or alpha power density or delta power density from resting state EEG. I see that it's very important to have this kind of comparisons also for clinical applications and the selection of the optimal features for machine learning, for prediction of clinical trajectories or for classification of individuals. But I suggest that you also try to use not only global alpha power density measures or delta power measures, because we know that there is some topographic aspects of these rhythms. For example, for alpha, the occipital or parietal channels can convey the alpha rings from the visual system, and so ideally you could maybe improve the performance of linear measures if you exploited the spatial features of alpha or other frequency bands, just to give the chance to linear measures to
No, no,
compete with the
absolutely.
fractal dimension
No,
values and so forth.
absolutely, absolutely. You are right. There is also this story of the alpha one, alpha two, beta one, beta two. You are right. To be honest, all the time that, and at least all the time that we are doing this nonlinear method, we are always taking a linear. A linear approach like the frequency band. Now here I didn't show the topography, but there is other study where we show the topography and we can make the difference across the topography where we have differences. It doesn't mean that you have a global activity. The global activity might be is when you have a very strong difference. But when you have a tiny difference, if you put all the channel together, of course, you reduce the difference that you can find in the occipital part or the motor part and whatever. So absolutely right. I'm fully agree with you that probably the topography, but also the bands should be used more clearly, like alpha 1 and alpha 2 that we know that have two different circuits. So absolutely agree with you.
Yeah, and a final comment is on the clinical relevance of the fractal dimension values that maybe you can try to demonstrate with some correlations with the clinical features of your patients. For
Yeah.
example, the cognitive performance, the cognitive
You are
status,
right.
or also the motor
Yeah, yeah,
symptoms or other specific features of your patients.
absolutely. You are right. Yes, in the paper that I show, you find the correlation that we have with the clinical uh, feature and also cognitive task in the study. So this in the publication that I show, but I didn't show in the presentation, but they are there. So there is a lot of correlation, and seems that the correlation is always better respect to the frequency band. But the problem in this is just brainstorming. I'm not really sure, but when we correlate alpha with a clinical scale, and after we correlate beta, since we found that the HFD is a combination, not a kind of combination between multiple frequency band, this is the reason, in my opinion, why the HFD always correlate better with the clinical scale, because it's something that is taking alpha and beta. Maybe with alpha you have correlation 0.5, with beta you have correlation with 0.4, but if you use HFD that make the combination of them, you have correlation 0.7. So this is
Yeah,
what we
this
already
is
find.
right. But for example, you see that from linear tools, you can apply also the amplitude coupling or phase
Yeah,
amplitude
yeah,
coupling or
absolutely.
bispectrum or bicoherence,
Yeah,
providing the information about the covariance or associations across frequency bands also in that sense. And also the relative power density in some way you have in each frequency band the impact also of the power in the other bands, no? When you have the relative
yeah,
power
yeah.
and the normalization. So in some sense,
Yeah, yeah. So if I was a student and you are making this question like a professor, my answer was yeah. But if you have to use the other index, you have to move from the time to frequency domain instead. With the HFD, we stay in time domain, so we don't have to make any a different transformation. Remember that when we make filter, even when we make a filter in narrow bands like delta, beta, especially if we divide alpha in alpha 1 and alpha 2, or beta 1 and beta 2. So we are going to induce to the data a kind of fake oscillation. Then you are altering the data. So you are saying that they are oscillating. So you are introducing an error in some way. But I understand that there is many other things. So if you want to think like HFD is like one number that express a value of a time series. Instead, when you move in the frequency band, you have 5, 6, 7, 8 um, feature that express the same time frequency. And of course, if you have just one number, the number is more rough respect to the 5 or 6 because they are decomposed in bands, phase, no phase. I don't say, I'm not saying that one is better respect to the other. What I say in the last part of the talk is that we need both of them, because since that in the EEG data, we have one part that is oscillation and one part that is a burst. So when we have a burst and we make the frequency, we are averaging, then we are deleting the burst. And then we are, let's say, just looking for the linear part. Instead, when we decompose the data, we say in the non-oscillatory part, so the parts, we are using the nonlinear, so the fractality. So if we are able in some way to combine both of them, we have more information from the data. So we have the linear and nonlinear part. So we have to use both.
Yeah. I fully agree with this conclusion. Just to come to your last comment, that we go to with the spectral analysis of EEG signal, because we know that there is an oscillatory behavior of neural populations on the thalamic and the cortical level, no? Because we see that they follow this frequency pace. Yeah. No, and so we profit from for example, the experiments and findings of Vincenzo Crunelli's group in Cardiff, showing that the peak of alpha oscillation in the local field potentials are at the same time of the spiking of the thalamic neurons. And so this is why we go to frequency domain with all the limitation that you express. So thanks again for this really exciting presentation and very insightful discussion. And
Thank you.
the last word on Florinda Ferreri, and I cannot forget the enthusiasm of Florinda in May 2 years ago, so a couple of months before the disease manifestation, talking with enthusiasm of your enrollment in the University of Padua. And she experienced this event as a big success of the neurophysiology unit in the Department of Neuroscience in the University of Padua. And so I'm very happy that you could have this talk this year. Thank you very much to all for
I really appreciate it. I really want to say that.
Again.
Thank you. I have to say that when I come here in Padua, I was also very exciting, and we start to plan with Florinda many bridges. We have to do this, we have to do that, we have to make this, we have to make that. We said we have to replicate what they do in Rome, because we know that Rome is super good for electrophysiology. And we said now we have the time and the power to do something to replicate what is the School of Electrophysiology in Rome. Unfortunately, the time was not enough, but I tried to do my best in her memory. Thank you.
Thank you very much. Thank you very much. Bye-bye.
Bye. Thank you.